Welcome to the Chapter 6 and 7 Homework Solutions screencast. Welcome, all physics students. Anyhow, there's quite a few problems here and questions, obviously. So I want to go through those as best we can. The magic word for the day, if you listen to the screencast, the first person who tells me this might get a bonus. I don't know. The magic word for the day is perfunctory. Perfunctory. I'm not even sure what it means. Hey, someone there is messaging me, and I'm going to silence it. Okay. These are the questions out of Chapter 6, so they're fairly straightforward. This was in a box was shot off of a giant rubber band. The weight is 0 as soon as it's shot off because weight is just a measure of the normal force in this case. So it's a measurement. In this case, this is a book sitting on a table. Someone's pushing down the book. The normal force is greater than the weight because the normal force has to oppose both the weight and the applied force. These are problems. So problems with Chapter 6. This is a force diagram or a weight of person on an elevator. They start on the 50th floor. And you need to find out whether they go down or up first. So they're going to go down because it looks at this long period of time, which seems like it would be a constant velocity. They have a 750 Newton weight. So in part B, if I use 10 newtons per kilogram, that gets me that they have a mass of 75 kilograms. And this indicates an acceleration downward. This indication indicates an acceleration upward. So if they're losing 150 newtons, then that indicates that they're moving downward at 2 meters per second squared. So basically you get the weight, which is the normal force, is m times g minus a. So if we have an acceleration downward of 2 meters per second squared, 10 minus 2 is 8. 8 times 75 gets us 600 newtons. So part C is asking about the displacement during the trip. I initially can figure out that this is accelerating downward at 2 meters per second squared for 2 seconds, then a constant speed, and then accelerating upward as it slows down at 2 meters per second squared also. So there's a symmetry to this problem. I can use this formula to figure out the displacement during the first 2 seconds. That's 4 meters. Here it's going 4 meters per second for an 8-second interval. That's 32 meters. And then you could use this complex version of this kinematics formula, or you could recognize the symmetry between 10 to 12 seconds and 0 to 2 seconds and recognize that we also would have another 4 meters of displacement. So that's a total displacement of 40 meters. 33, I think, is a good problem. So there's a point of interest right here. And at that point, you know the summation of the vertical forces and the horizontal forces is 0. The tension of the string can be found by just looking at the weight, the gravitational force acting on the 6 kilogram box, and that's going to be 58.8 newtons, and therefore the tension in the rope everywhere is going to be 58.8 newtons. So in this part, I want to look at here the vertical forces. So I know this angle, I know the tension in the string there, and I know the mass of the foot. So the upward force caused by the tension, the component of the vertical component of the tension in this string needs to equal the downward force caused by the weight of the foot and the vertical component of the tension in this string. So I've got force up is T sine theta, and I don't know what theta is. Force down, mg of the foot, and the tension times the sine of 15 degrees, which is the vertical component of this. So you get 58.8 sine theta equals 54.4. Do some rearranging algebraically. Inverse sine 54.4 over 58.8, and that's a 67.7 degree angle. Now, if I want to find out how much traction there is, really what the goal of traction is to pull directly out on this so that the bones don't set in a bad alignment. Kind of painful, I think. So it allows the bones to heal initially while they're in the right shape. I don't think it's used very much anymore. So force to the right would be equal to the tension times the cosine of 67 degrees for 7 degrees for this part, and the cosine of 15 degrees for that part. So I add those up, and I get about 79 newtons of traction. For problem 35, you're given a position formula. If you know how to use the power rule to take the derivative of that to get velocity, and the derivative of the velocity formula to get acceleration, and you multiply that acceleration by the mass, that would get you the net force. So at t equals 0 seconds, the acceleration is negative 6 meters per second squared. At t equals 1 second, it's positive 6 meters per second squared. So we get negative 12 newtons and 12 newtons. Just trying to keep calculus a little bit in our minds. For problem 55, wood block on a wall. There's a force directed up and to the left at a 30-degree angle from the horizontal. So the normal force is going to equal the horizontal component of that 12 newtons. That's 10.39 newtons. Gravity acts down, so that's going to be 9.8 newtons. And there's a vertical force up caused by the vertical force of this component of this force. So that's 12 times the sine of 30 degrees, which is 6 newtons up. It said wood on wood is the block on the wall. And so what you need to think about is that use table 6.1 to find mu. And that'll help you out. Anyhow, when I ended up doing that, I found it was 0.50. And so 0.50 times the normal force, which is around 10.4 newtons, is about 5.2 newtons. So since the downward force is 9.8 and the upward force is 6, the difference between those is less than the maximum amount of static friction, which is 5.2 newtons. So the book will not move, and friction would act upward. Friction would actually act upward with 3.8 newtons of force. Hey, I screwed up here, and I was starting to do the problems instead of the questions, so I'm going to come back to that. And you can tell I continued that, and that looks horrible. It looks like someone's hanging from something. So for question 9, it's talking about a tug-of-war, and basically the team that wins is the team that gets better traction with the ground or has more normal force with the ground. This is kind of a goofy question. So basically it shows a magnet being attracted to a cart. That's a metal cart. The magnet will not make the cart move because both of the magnet and the cart are part of the same system, and so the forces are internal. And that was when I squished a bug that was in my room when I was doing these problems, and so that's bloody bug guts. Scanned pretty well. Question 12 was asking what the reading of the spring scale would be in kilograms. Well, there's no acceleration, so therefore the tension has to be 5 kilograms. If there was anything other than 5 kilograms of tension, there would be a net acceleration of those blocks. Problem 9, done accidentally 2 pages ago, is up here. So we have a 1,000 kilogram car pushing a 2,000 kilogram truck, and then 4,500 newtons of the force of the car against the ground. Or the ground, so that means that there's a 4,500 newton force of the ground against the car. So that's the net force pushing the car-truck system. So I can figure out the acceleration of the car-truck system is 1.5 meters per second. And then, using that and the idea of acceleration constraints, I can figure out the net force on the truck. That's MA of the truck, that's 3,000 newtons. And therefore the force of the truck on the car also be 3,000 newtons. If you think back to the net forces on both of them, based on their masses, it would result in both accelerating at 1.5 meters per second. Going down here, problem 18, you had a cat here and a dog hanging here. I didn't draw those because that's horrible. And I have a tension here, tension 2 here, tension 3 here. We were given the fact that this angle is 20 degrees. We're asked to find angle and magnitude of tension 3. Well, to do that, we need to find tension 1 and tension 2 first. So I'm kind of starting from this left side and working over here to the right side. So this is the first point of interest, and at that point, the summation of the vertical and horizontal forces is 0. So I'm going to start by looking at the vertical forces. And I'm going to say that the force down is mg, so that's 2 times 9.8, 19.6 newtons. The upward force is T1 sine of 20 degrees, and I was given that this is 20 degrees. So that allows me to figure out T1 is 57.3 newtons. Now, that lets me figure out T2, because T2 is horizontal, so I can get the horizontal component of T1, 57.3 times the cos of 20 degrees, and that would equal T2, and that's 53.8 newtons. Now I'm going to the second point of interest. T2 is pulling to the left at 53.8 newtons. T3 is pulling up and to the right. Well, there's a vertical force down of m times g, 4 times 9.8, that's 39.2 newtons. So when I look at this, the summation of the horizontal forces and the summation of vertical forces, they've both got to be 0. So I have force left equals T3 cosine of theta 3, and force down is equal to T3 sine theta 3, which is pulling up. So I can rearrange this and solve for T3 is equal to this, and T3 is equal to this. Therefore, I could set them equal to each other. 53.8 over cosine theta 3 is equal to 39.2 over sine theta 3. And I can rearrange that and get that sine theta 3 over cosine theta 3 is equal to 39.2 over 53.8. Sine over cosine is the same as tangent. So theta 3 is equal to inverse tangent 39.2 over 53.8, and that's a 36.1 degree angle. Plug that back into either of these equations. I started to do this one, and then this one was close to the side of the page. So plug that angle into either side of the equation. I can solve for T3, and that was about 66.6 newtons. Problem 27, you have a starship and a shuttlecraft, and there's a tractor beam, and it's asking you to determine how far the ship moves as it is pulling in the tractor beam. So this is a little subtle because the ship has 100 times the mass of the shuttlecraft. The distance between them is 10,000 meters or 10 kilometers. So basically what you need to look at is the net force of the tractor beam, and that would cause a certain acceleration on the shuttle and a certain acceleration on the ship. Therefore, the relative motion between them is going to be an acceleration of 2.02 meters per second squared. When I plug that in, that gets me that the time that they're going to be accelerating before they collide would be 99.5 seconds. Now, if you didn't take into account that the fact that the ship was also accelerating, you get this to be 100 seconds. So it's just a little bit off. And so therefore, this ends up being about 99 meters. I think it might have been 99.5. Oh no, 99.5 squared times that. So that's 99 meters. That means that the shuttlecraft moved around 9,901 meter. And the spaceship or the starship moved about 99 meters. So a little subtlety there. This, I feel bad for Jax. Concussion. You gotta wear a helmet, man. So it says that the forehead can withstand 6,000 newtons and the cheek can withstand 1,300 newtons. There's a ball, baseball, mass of 0.140 kilograms. Could have been a lacrosse ball, who knows. And it goes from 30 meters per second to 0 in about 1.5 milliseconds, so that's 0.0015 seconds. So that's a magnitude of acceleration of 20,000 meters per second squared. So when you apply that with that mass, it's 2,800 newtons of force of the ball on the person as well as the person on the ball. So that would not fracture the head, would fracture a cheek. So Jax, be glad he didn't get hit in the cheek. This one I will probably go over in class. I think it's important. So I'm going to come back to that in just a minute. 46 is a bosun's chair. Basically, there's two forces up. The person and the chair have a total mass of 80 kilograms. The person in the chair is accelerating upward at 0.2 meters per second squared. So essentially, I need a net force upward of 18 newtons. To draw a free body diagram, I've got two tensions upward because the rope is on the chair and the person is holding the rope. So the idea is that a pulley is actually going to be a simple machine. It's going to reduce the amount of force you need because you're applying that force at two different points. I think there's a Smarter Everyday video on snatch blocks, which is really pretty cool. It deals with pulleys and things like that. So if I do this free body diagram, then the idea is it's 2t minus this mg is going to equal to mass times the acceleration. So 2t minus the weight, or the gravitational force, pardon me, is going to equal 80 times 0.2, which I already said was, ooh, that's 16 newtons. Dang. think I'm gonna change that while you're not looking. I hate it when I do that. Someone will find it. Okay, well, anyhow. 784, 2T minus 784 is equal to 16. So that tension is 400 newtons up in each of the chords. Coming back to this. This looks like a toilet paper roll, but I'm not at good drawing. This is sneaky because you've got a block on the ground. You're applying a 20 Newton force to it. A block on top of the first block. The coefficient of friction between the two blocks is 0.3, and the coefficient of friction between this block and the surface is 0.3. So you might be thinking, oh, well, there's friction. Yep, there is, and it matters. So you can't just do 20 newtons divided by 3. But there's actually 3 friction interactions. There's the friction of the surface on the larger block. Well, that's mu times mg, and that m is the mass of both blocks because that's the normal force on this surface. That's 8.82 newtons, and that's acting to the left on this block because it is accelerating to the right. Force of friction 2 is going to be the interaction between these two blocks. That's mu mg, so 1 kilogram times 9.8 times 0.3, and that is also acting on this lower block from the upper block. So I call it block 1 and block 2, and that would be acting to the left to try to slow it down. But because the friction between the two blocks is actually an interactive force pair, friction of block 2 on block 1 and friction of block 1 on block 2, there's also a force of friction of block 2 on block 1, the same magnitude, acting to slow down or oppose block 1's motion, which would be accelerating to the left. So that force of friction is to the right on this top block. Either way, all 3 of these oppose motion, so I've got 20 minus 8.82 minus 2.94 minus 2.94 equals over 3 kilograms. That's 1.77 meters per second squared. So that is a lot of frictions there, but this is a very good thinking problem. Ooh, what if there was friction on the pulley? That would be exciting. Anyhow, these are a lot of problems. I hope you take the time to go through some of these answers if we don't get through them in class.